There is a lot of overlap between this topic that we're doing and the differentiation topic that we did at the end of last term. And so this kind of stuff here we have looked at before. So we're doing exponential rates using base E. So we did rates when we learned that a rate means to find the derivative of something. Okay, so the only thing is we're just going to have our base E because we've been focusing on exponentials and logarithms of base E. So here it is again. Yeah? All right, so example number 1. And extension people, you've done so much. Well, you should have done so much of this. Anyway, we won't go there. All right. Example number 1. The number B of bacteria in a laboratory culture is growing according to the formula B equals 7,000 e to the 0.2 t, where t is the time in hours after the experiment has started. Answer these questions correct to 3 significant figures. How many bacteria are there after 4 hours? So I'm using my equation, B equals 7,000 e to the 0.2 t. T stands for time in hours, and I'm told that I want to find the bacteria after 4 hours. I'm just subbing in that t is equal to 4. So you can write that here as a reminder. When t equals 4, we're going to sub that in. B equals 7,000 e to the 0.2 times 4. And then calculate in the calculator. Can't speak. Sorry, I'm getting a bit croaky. Okay, 7,000 times e. Whoops. E to the power of 0.2 times 4. And for 3 significant figures we need. So that will be the 1, the 5, the 5, and the 7. After the 7's an 8. So we're going to round up to be 1, 5, 5, 8, 0. And this is the number of bacteria. Was it 4 significant figures or 3? That's 3. All right, sorry, go back a bit more. So it should be 600. Part B, find the rate. So rate we know means differentiate and even gives it away again, dB over dt, derivative, at which the number of bacteria is increasing, and show that dB over dt is equal to 0.2b. All right, so dB over dt, the derivative of b with respect to time. We're looking at, I'll highlight it, this equation here, b equals that one. Remember, when you're differentiating an exponential, you take the derivative of the power, so the derivative of 0.2t is 0.2, and you want to times it with whatever is out the front. So that is 7,000 times 0.2. Then the exponential part, the power stays the same. You don't subtract anything, so 0.2t. Now that makes 0.2 times 7,000 is 1400 e to 0.2t. So I have found the rate at which it is increasing, but I am also asked to show that it is equal to 0.2 times b. Now back in the first line of working out, this part and that part, the 7,000 e to the 0.02t, those two parts there, that is what b was equal to. Okay, so you're really just saying these bits are b, and I've got 0.2 times by a b. So it is the same as having 0.2 lots of b. Yeah? Part C. At what rate are the bacteria increasing after 4 hours? We've already done how many bacteria are there at 4 hours, but this is the rate at 4 hours. So we're subbing t equals 4 into the derivative. When t equals 4 into the dB over dt, we get 1400 e to the 0.2 times 4. And then you type that in your calculator. And we're meant to be doing 3 significant figures. So that comes out to be 3120. And we need to work out what the units are going to be. The dB, B stands for bacteria. So the first part is going to be bacteria. And it's over dt, which is time, and our time unit is in hours, so it's bacteria per hour. So it's increasing at 3,120 bacteria per hour. Part D, what is the average rate of increase over the first 4 hours? Remember, in our last topic, when we differentiate, we are finding the instantaneous rate. We're finding the rate at a particular or one particular point. If we are asked for an average rate, we're actually trying to find the gradient between 2 points. So in this case, the average rate over the first 4 hours is going to be from the starting point to time equals 4. The starting point, when time equals 0, we have, I'm about to write it. How many bacteria do we have at time equals 0? 7,000. So that's my first point. At time equals 4, how many bacteria do we have? Yes, that's the one we found in part A. Okay, so there is my 2 points. So the average rate is going to be using the gradient through 2 points, y2 take y1 over x2 take x1. And we sub in from those points. So y2 is 15600 minus y1, which is 7,000, over 4 take away 0. Has anyone calculated that? Oh, I think I heard, what did you say, 8,600? Oh, what did I forget? Uh-oh.
2,100.
Let's see if I get it right this time. There we go. 2,150. Again, this is a rate, and we know that that is bacteria per hour. dB over dt, bacteria per hour. Part E, when are there 8,000 bacteria? So I'm wanting to make the number of bacteria, which is B, equal to 8,000. And I want to solve that to find, if I ask when, that's asking you to find the time. At what time is it going to get to 8,000 bacteria? So into our original one up there in yellow, subbing B is 8,000. I will get 8,000 equals 7,000 e to the 0.2 t. And this is where our fun with rearranging things begins. I want to find out what t equals. So first of all, divide the 7,000 across the other side. 8,000 divided by 7,000, it's just going to be 8 over 7. Now to get the t, which is in a power, I'm going to have to do a sliding base. Okay, so 0.2 is going to stay by itself. The base e is going to slide across to be a log base e, or in other words, ln, of 8 over 7. Remember the sliding base? And then finally, I just want to get the t completely by itself, which means I have to divide that 0.2. So it's ln, I'm running out of room here. I'm dividing that by 0.2, and I want 3 significant figures. Has anyone typed it in?
0.67.
Excellent. Now this is time that I found, so that unit is going to be in hours. You could change that into minutes if you wanted to know what that was, but leaving it in the units we're given is fine. Part F. When are the bacteria increasing by 8,000 per hour? Increasing is the rate. So now I want to put in that dB over dt is equal to 8,000, and I want to find the time then. So my dB over dt is way back up here in part B, that equation there. Okay, so I'm putting the 8,000 in. 8,000 equals 1,400 e to the 0.2 t. And then we go through the same process again of trying to get that t by itself. So divide the 1,400 and you should get 40 over 7. Don't go into decimal form until the very end, okay? You don't want to turn that into a decimal and have rounding errors in there. So now do a sliding base. So I have my 0.2 t equals log base e, or ln, of 40 over 7. And then I just want to divide my 0.2 across. I'm just going to go, so I don't have to write another line, but divide that, divide my 0.2. So t is equal to, anyone get an answer?
8.71.
8.71 hours. Okay? So not really anything new there, was there?